Hello friends, welcome to Refraction of Light Part 2. In previous lecture, we learnt about refractive index, total internal reflection and so many phenomena. In this lecture, we will learn about refraction by spherical lenses. The refraction by spherical lenses. So what are spherical lenses means? Lenses whose refraction surfaces are spherical are called spherical lenses. A spherical lenses whose refracting surfaces are bulged outward. This is a bulged outward here. See, these two bulged outward. When this is bulged outward, and at the center and thin at the edges, such type of lenses are called double convex lenses. Such lenses are called what? Double convex lenses. And few lenses have at the center, middle thin, and here at the edges are bulged. These are known as concave lens. These are known as concave lens. And there are so many varieties of lenses here. See, biconcave, biconvex, plano-concave. Plano-concave means this is the plane, and plano-convex, this is the plane and this is the convex surface. And now what we have, concavo-convex and convexo-concave. A spherical lens whose refracting surfaces are curved inward at the center is called a double concave lens. It is thinner in the middle, just we discussed. Different types of spherical lenses also we have seen. And this is the actual picture of a lens. This is the convex lens and this is the concave lens. See, the outer edge is wider and bulged and thicker, whereas the inner at the center is thin. And here this is the thick at the middle at the center, and here is the thinner. So these are the two lenses, concave and convex lenses. And generally the convex lens and concave lens, diagrammatically we will show like this, and this lens is called converging lens and this lens is called diverging lens. Why this is called converging lens? When the parallel beam of rays are passing through incident on the convex lens, after refraction they meet at a point, means the rays are bending and meeting towards, means this is called converging. The beam is converged, and whereas the beam is diverged here. Here these rays are diverging. Here is the rays diverging. This is the incident beam of light and these are diverging. Here convex lenses and concave lenses, when we are talking about a few important points, terminology we should know. This is the convex lens representation, and here F, F, C, C. Instead of C, we have to better mention 2F. The same thing in case of concave lens. So the line passing through the center of the lenses are called principal axis. This is normal to the curved surface and passing through the optic center. The center point is called optic center. Here O is known as optic center. The line, imaginary line which passes through this optic center and normal to the this one is called simply principal axis, and F is the focus, C is the center of curvature. In general, what I said, we have to mention it is 2F, and the distance from optic center to F is known as focal length, and here is nothing but radius of curvature, center of curvature to this curved portion, refracting surface. This is known as radius of curvature. So optic center, there are two centers of curvature on both sides of the curved surfaces, and a principal axis. After the principal axis, we are having the terms that is known as principal focus. What is exactly the definition of the principal focus? It is the point on the principal axis at which the incident rays of light parallel to the principal axis either really passes through or appear to pass through after getting refracted from the lens. Here the term here we are using in case of convex lens, the parallel beam of paraxial lines. Okay, paraxial means very close to the principal axis. These rays, when passing through the convex lens, they meet at a point on the principal axis. They passes through a single point. That concurrent point is known as principal focus. A lens has two principal focuses. What is that those two, F1, F2, F1 and F2. The parallel beam of rays, see here diverging, it seems to be, this is the virtual focus. Concave lens has the virtual focus. The convex lens has the real focus. The focal length is the distance between the optic center and the principal focus. In case of mirror, the radius of curvature r is equal to 2f. In few cases only this r is equal to 2f holds in the case of lenses. There are so many possibilities. Even we can show numerically in certain lenses r is equal to f. So we will discuss it separately. Now, when we are talking about this, how to get the image, what is the image position by these two lenses, what are the various rules related to certain three principles we are using. Based on that, we are obtaining the position of image. Here see, the ray which is parallel to the principal axis on refraction passes through the focus. This is the first condition. Whenever a parallel ray passes through the lens, it always seems to be passes through the focus, either real, it passes, virtual, it seems to be. Okay, coming from that focus, virtual focus. The second rule says that the ray, incident ray, whenever passing through optic center, no deviation, without deviation, it moves, it goes, it passes. And the ray which is coming from the focus on refraction become parallel to the principal axis. See, this one and this one are converse, we can say mathematically. The parallel ray passes through focus. The ray coming from the focus become parallel to the principal axis. Now, by these 1, 2, 3, we can locate, we can find the image position formed. So these three rays, because there are many rays are emit from the object, the source, but generally pictorially we will represent only two, because we don't want to clumsy all these rays showing, putting together. So we always use, while we are finding out the image formation, position, nature, everything, we are only taking two rays, either 1, 2, 3, either of these three. So this is the intersection point, gives us the image position. Here in the picture, the object is kept at various positions. We are getting the images. See, the sizes are also different, the position of the images are different. See, here see, these two are inverted, and whereas these two are erected. So all these properties one by one we will discuss, but after that we will tabulate it. What gives that one? Say the first case. In this case, when the object is placed, means the source is kept here AB, then the parallel ray is passes through its focus. And the second ray, that what we discussed, when it is passing through optic center without deviation. So they never meet, these two rays never intersect, X and Y never intersect. So it seems to be, when the observer is visualizing this, observing this, it seems to be these two are coming from some point here. So this is the virtual position of the point A. So A dash is the image of A. Similarly, B dash is the image of B. We can show this one. So in this case, when the object is placed between optic center and focus, the image is formed on the same side of the object, erected, magnified, but it is virtual. We cannot collect on the screen, because object side the image is forming. We are viewing the other side. So it is not possible to collect on the screen. So this image is a virtual image, but magnified, erected. When we see the second condition, in this condition, the object is exactly placed at the focus, one of the focus, principal focus. So the ray parallel, the same type of rays we are taking. One is the parallel to the principal axis, and the one is passing through the center O. So when we are taking these two become parallel. In the previous case, these two rays are not parallel, they are widening apart, they widen apart, but here these two become parallel. So they never intersect. So then where will be the image formed? Object, when we are keeping on the principal focus, image formed at infinity. These two parallel rays meet at infinity, so the image is formed at infinity, highly magnified, inverted, okay, and real. Next, when we are talking the case width, we are moving further. See, the first case between F and C, the second case we have taken at F. Now the third case, we are keeping the object AB in between 2F and F. When we are keeping this AB in between, the same two rays we are taking, one is the parallel and the one is the passing through the optic center. These two intersect at A dash. So A dash is the image of A. A dash is the image of the A. And similarly we show the B image B dash. So you may question us, sir, how it is possible here these two rays are intersecting, but for the B it is not intersecting. Now see, if you consider the ray is passing through this optic center, without deviation it is going. Am I right? This is going on right as it is going on. So here it is not shown, but the rays are from the means from point B also the rays are emitted out coming. Now this is the B dash and this is the B, and A, this image is A dash. So B dash A dash is the magnified image inverted forming beyond 2F. In between we are keeping that image is formed beyond 2F. So this is the real inverted and magnified image. So next we are going for this fourth case. So if you see, previously we kept in between 2F and F, but here we are keeping exactly 2F. The same rays when we are talking about one is passing through optic center and the one is the parallel. So these two meeting at this point. Okay. So now this size and this is the size, both are equal. Means image properties when we are talking about, when we are taking a 2F2, matlab one of the center of curvature we can say 2F2, then here it forms exactly other side 2F distance, and this is whatever we are talking about inverted, real and same size. In the previous case, here see, when we are talking this is at infinity, here it is forming in between. Now when here it is the same size it is forming, same size it is forming. The next it is diminishing, means at infinity it is so much enlarged, and the next case it is enlarged, and in the above case it is equal size. Now this size is diminished. But where we are taking the position is beyond 2F. When we are taking it the beyond 2F, we are getting an image at B A dash B dash, which is in between F and 2F, in between F and 2F. Here also it is inverted, diminished, real. Except the first case, in all the other cases we are getting the real image, that is object is one side, image is the other side. And in the first and up to these cases, if you see, the object is taken away from the optic center. First we are taken in between F and O, next we have taken at F, the next F and 2F in between, the next at 2F. Now this is the case beyond 2F. So in all the cases, if you observe, the image is moving from infinity to here. The final case, if even we are taking away from beyond 2F and further if you are moving to infinity, then the size is gradually decreases, and finally the image format focus a diminished real inverted image, real inverted image. So here are the few cases we can see to understand better. This is the converging lens, a real image when it is forming. This is the converging lens, virtual image it is when it is forming, and this is the diverging lens, virtual image forming. But in case of diverging lens, wherever you are keeping the object, whatever the position, whatever we discussed in 6 cases, in any case if you keep, we get always diminished, erected and virtual image. This is the real image formation cases. This is the virtual image case. In case of convex lens, this is concave lens. The concave lens always form virtual image. Next we are talking about lens formula. What is lens formula? 1 by f is equal to 1 by v minus 1 by u. What are v and u? This is the v is the image distance, u is the object distance, f is the focal length of the lens. The sign convention, the measurements, I will explain you later. Now the next step, we are going for the linear magnification. What is linear magnification? Why we are using? In the previous slide we have seen, what we have seen, simply a small ant is observed by using a magnifying glass. Magnifying glass is nothing but a biconvex lens, equiconvex lens, which we know is magnify the image of the object. It magnifies the image of the object. So that is the purpose. This is when we are getting this size magnified, object and image both are same side. So this is the first case, of course. So this is called linear magnification. Now the linear magnification produced by a lens is defined as the ratio of the size of image to the size of the object. Next, magnification produced by a lens is also defined as the ratio of the image distance to the object distance. So we can define either ways. So there is a reason the linear magnification M is the ratio of V by U or the ratio of image height to the object height. Even we can express the magnification in terms of V and F in the numericals when U is not given, not known. Similarly, if U is given and V is not known, F is given, then we can use this one. Okay, magnification means this is the mathematically we can obtain by using a lens formula. Next, the most important is nothing but power of lens. The power of a lens is the ability to bend a ray of light falling on it and is reciprocal of its focal length. Exact definition: the degree of convergence or divergence, the degree of convergence or divergence of a lens is simply its power. Generally in our class 10th, we will write this reciprocal of focal length. When the focal length is in meters, the power of the lens is having units called diopter. So when the focal length is expressed in meter, then P is expressed in diopters. Now the sign convention part, and how can we take while going to the numericals, 1 by f is equal to 1 by v minus 1 by u. Then how to do here? See, if you see, all the distances are measured from optic center. Either whatever the lens we are taking, all the distances are measured from optic center. The rays are the, suppose this is the object, the rays are falling like this. This is the object, rays is falling. Now the distance is measured. The distance is measured in case of, suppose we want to measure the distance of an object. Where is the object? Here is the object. Suppose the distance is measured from optic center to this object, which is opposite to the ray of incidence. So incident ray, this is opposite. Hence those distances which are opposite to the incident ray is taken as negative. Those distances which are measured in the same direction of incident ray is positive. The convex lens, U is always negative. In case of concave, U is also always negative. In case of image, in case of real, in case of virtual, in case of real and virtual, see, real, the image is formed this side, not on the same side of the object. So the distance measured to V is measured from optic center to the image position. So this is along the direction of incident ray, so this is positive here. Okay, in case of virtual, the final image formed on the same direction, so which is opposite to the incident ray, negative. So these are the positive distances, these are the negative distances. Same in case of concave lens, these are the negative distances and these are the positive distances. And the heights measured, up is positive and down is negative. So these are the, basically we are having sign conventions. Whenever we are going to solve the numericals, we must follow these, what you call these sign conventions. We will see the numericals on part 3. Thank you for patience listening. Like and subscribe my channel.